Good evening. I'm Doug Arnold. I'm the director of the Institute for Mathematics and its Applications, which brings you this series of lectures, and this is the fourth and final one for this year, Math Matters. I'm delighted today to have with us Jennifer Chayes. Jennifer studied biology and physics at Wesleyan and then got her PhD in mathematical physics from Princeton in 1983. Went on to postdocs in Harvard and Cornell, and then spent much of her career on the faculty of the mathematics department at UCLA, with a variety of visiting positions, including the Institute for Advanced Studies at Princeton. In 1997, she was recruited away from UCLA to Microsoft, along with her husband, Christian Borgs, and together they founded the Microsoft Theory Group, which is, as Jennifer puts it, the part of Microsoft that does research for the day after tomorrow. Dr. Chayes continues to co-manage the Theory Group at Microsoft, and she's helped to build it in 10 years into an unbelievable research group in the area of discrete mathematics, theoretical computer science, and mathematical physics, and the interface between those fields. It's really unique in the corporate world, a research center of the nature of the Microsoft Theory Group. The areas in which it specializes in are also the areas in which Jennifer is a leading expert. She's particularly associated with phase transitions, and she's someone who serves to define new fields and emerging fields and point out the new directions. At Microsoft, she also holds the position of Research Area Manager for Mathematics and is heading a new group called Algorithms, Computation, and E-Commerce. She's also an affiliated professor of mathematics and physics at the University of Washington. She's published more than 80 papers, is an inventor on 11 patents. She's widely sought out as an advisor and a leader. She's served on the advisory boards of most of the major mathematics and computer science institutions. I'm happy to say she served on the advisory board of the IMA in the past. She's been honored in many ways, including as a fellow of the American Association for the Advancement of Science, and she was the chair of the mathematics section of the AAAS. She's also very active with the National Research Council and the National Academies, to which she's been named a National Associate. And finally, she's well known as a terrific communicator, so I'm really glad to have her, and I won't keep her any longer. So I bring to you Jennifer Chayes, who will be talking about epidemics in technological and social networks, the downside of 6 degrees of separation. Jennifer?
Hi. So I'd like to thank the IMA for the invitation to speak here, and I'd like to thank Doug for that wonderful introduction. I'd like to meet me after he says all that stuff. So, okay. So what I'm going to do is, there will be some math in here, but I'll try to translate it, okay? But I'll talk about something. Oh, is the meet-in group here or not? Yeah? Okay, yay. So there are some people who are actually here from an online social network. So I was excited about that. They wrote to me yesterday and said that they were coming. So what I'm going to do is I'm going to talk about epidemics, so you guys should watch out, in technological and social networks. And this is the downside of 6 degrees of separation. We know a lot about the upside, so this is going to be something about the downside. So what I'm going to do first is to tell you about the internet, the World Wide Web, and other power law networks. Then I'm going to tell you what models we use for the spread of viruses and worms. This can be on a technological network, or we could also talk about the spread of a virus on a social network. And then finally, I'm going to put the two of them together, and I'm going to talk about epidemics on power law networks. So when we take the models of the networks and put them together with the models of the virus spread, we start to look at models of viral spread on these kinds of networks and how we can get epidemics on the networks, and hopefully how we can also control the epidemics on those networks. And it's the last part here that may have a little more math in it, but hopefully you don't really have to look at the math that much. Although if you like math, it's kind of nice to look at. Okay. So in this part of the talk, first I'll tell you about the internet and the World Wide Web and how we view them as graphs. This is actually very important for things that you use all the time, like search engines. The basic search engine algorithms are built by viewing the World Wide Web as a graph. Then I'm going to talk about some of the observed properties of the internet and the World Wide Web. I'll talk a little bit about social power law networks. And then we'll look at the mathematical models of these networks. So here is a snapshot. This is an actual snapshot of the internet. It's somewhat old, so this isn't as large as it would look now. I can't give you a snapshot of the World Wide Web, which the best estimates say that it's got about 100 billion pages now, 100 billion sites. So this is a really tiny piece. And one of the main differences is that the edges here go from one site to another site. Here, if site A is connected to site B, then site B is also connected to site A. But on the World Wide Web, if I have a link to the CNN webpage, that doesn't mean that CNN links to my webpage. Okay? So we view these things as graphs, and a graph has a set of nodes or a set of vertices and a set of edges. So for the internet, the nodes are what are called the autonomous systems. So AOL and MSN and Yahoo and UNM.edu would be a node, okay? And then the edges are the fact that AOL does have a connection to MSN and Yahoo has a connection to umn.edu. Okay, for the World Wide Web, the vertices are just the web pages, and the edges are the hyperlinks. And as I said, those are directed. So right now, the IMA on one of its pages might have a link to my web page. But I might also have a link to the IMA's webpage. So we would have two links, one from me to the IMA and one from the IMA to me. And sometimes it would just be one way or the other way. Okay, so what are the observed properties? The first thing that got people pretty excited is that these kinds of networks have very small diameters. So what's the diameter of the network? It's the maximum length of the path from one site to another site on the network. So obviously, if the network breaks up into two pieces, I don't want to ask what the diameter is, because then it would be infinite, because I couldn't get from one piece to another piece. So let me look at the average distance over the connected pairs. And here are the numbers that people have measured. So for the AS internet, the average distance from one site to another site is really small. Now for the big sites that I told you about, AOL and Yahoo and MSN, those distances are all 1, but there are little autonomous systems, and those might have a larger distance. For the World Wide Web, if I allowed myself to go backwards over the hyperlinks, it would just be 6 steps, so like 6 degrees of separation. For the World Wide Web, in which I'm only allowed to follow the hyperlinks in the direction in which they're laid down, it's about 16. And so these are measurements from 1999 to 2000. And unfortunately, what has happened is that if you now know things about the web, it's considered really valuable information that you might be able to use to make money, like Google makes money and like Microsoft tries to make money on that. And so the observations are not released much anymore, which is why I told you about some old observations. Okay, so a second observed property is what's called clustering, okay? And so what this is, if I have some site X, okay, and I could also think of this, let's say, as a social network. So person X knows person X2, knows person X1, blah, blah, blah. What are the odds that person X2 knows person X3? okay? And if a graph is highly clustered, then the odds are pretty high, okay? Now, when you, so if I look at the set of nearest neighbors of a vertex X, the clustering coefficient is the number of edges in the neighborhood of X over the maximum number of possible edges, and that would be what you'd have if everybody knew everybody else, okay? But I mean, like, you know your aunt. That doesn't mean your friend knows your aunt, right? So you wouldn't expect a clustering coefficient of 1. And for the World Wide Web as an undirected graph, this is unbelievably big, okay? It's 10%. That's just huge when you think of the fact that there are about 100 billion web pages out there, okay? And so I look at my neighborhood, at all the pages that I'm connected to and all the pages that are connected to me. What are the odds that they're connected directly to each other? And that's about 10%. So there's really a lot of clustering on the World Wide Web, okay? Which is why all these companies are springing up that want to take advantage of this clustering, these social networks, this kind of viral marketing. They want you to, you know, try to sell things to the people you're near or pass music to the people you're near. Okay, another property is growth or aging. So this is a pretty obvious property. The sites that have been around longer tend to have more connections to them. I mean, obviously, if you've just put up your web page today, you know, you're not going to have as many links to it as you might have 5 months from now, okay? Now, this is just a trend, but it's really not the only thing. The number of connections also have to do with the quality of the site. There's a fitness in there also. So, for example, if it were just how old the site was, then we would all use Alta Vista as a search engine. We wouldn't use Google. So there's a quality parameter in that too. Okay, and some of us use MSN search. Anyway, another observed property is power law degree distribution. So this is one of the things that makes these kinds of networks so special. The probability that a node in one of these social networks, or something like the internet or the World Wide Web, has k neighbors falls off like k to a negative power, so like 1 over k to some power, okay? And you might think that that gets small pretty fast, but lots of the things that people look at actually have exponential decay. So let me show you what the difference is. This is a bell curve, and you see at the edges this falls off really, really rapidly. And if you had something like that, then most nodes would have the same number of neighbors in them. Whereas here, you've got a much longer tail. So people talk about long tails, scale invariance, power law networks, okay? And that means that there's some reasonable chance of having really highly connected nodes, like MySpace, okay, or AOL. Okay, so what are the observations of power law degree distributions? Well, actually, they go back now, I guess, 2 centuries. In economic models, Pareto, and people still talk about Pareto distributions, realized that wealth didn't fall off exponentially. It fell off like a power law. Okay, so there was, you know, some people who were really, really, really rich. Okay? Zipf in the late 1940s saw power laws in sociological networks, and you might have heard of Zipf's law. That had to do with this power law that he found in sociological networks. In 1999, people got really excited because the Faloutsos brothers, there were 3 Faloutsos brothers. In fact, there's a funny story here. A friend of mine, Christos Papadimitriou, was teaching an elementary probability course at Berkeley. And he was teaching people how to compute the probability of things. And one of the kids in the class who was sort of artsy, when he told them about this, this guy said, wow, what are the odds that 3 people with the same name would write a paper together? Thinking that it would have been independent, right? Which is why we should all learn a little bit of probability theory at least and know that it's different if things are dependent or independent. So, and these guys already knew each other. They were brothers, okay? In 1999 through 2000, people made some measurements of the World Wide Web, and as I said, people have been making a lot more measurements, but most of them are not published now because it costs many, many millions of dollars to do it, and companies keep it proprietary. So here, okay, there are different power laws for the in and the out degrees. So because I have 29 hyperlinks into my website, it doesn't mean I have 29 hyperlinks out of my website. I might have, 29 in and 15 out, okay? And so in general, for the whole web, there might be different power laws for the probability that you have K in links and the probability that you have M out links, okay? And there are different power laws, and what these different power laws tell us is that this one falls off more slowly. In other words, there are bigger odds of finding lots and lots of in-links. And why does that make sense? Because the sites that have lots and lots of links typically have lots and lots of in-links, okay? CNN, tons of people point to CNN. It doesn't mean that CNN points to as many pages as the number of pages that point to CNN. So you would expect this power law to be smaller, and indeed it seems to be. Okay.
In 1999, had link farms been invented yet?
So what she is talking about, link farms, I don't think that they had been invented because Google had not started and PageRank was not being used at that time. So what this woman is talking about is that right now, the basic algorithm that's used for search engines is that you have what's called a crawler, which takes a walk along these hyperlinks, follows these hyperlinks. And every now and then you start it again because you don't want it to get stuck, okay? And then what happens is that your page rank, so how high up you'll come on Google or Yahoo or MSN, will depend on how often the crawler lands up at your site. And obviously, if you have a lot of in-links to your site, the crawler's going to land up there more often. Okay? Now, if you have a business in which you're trying to sell shoes, okay, you're Zappos and you're trying to sell shoes, you would love it if there were more in-links, because then you'd come up higher without having to pay for advertising on search engines. So there are these businesses that came up called link farms where you pay them and they send a lot of links into you. And now the link farms have probably distorted this number, okay? And then what happens is, and I'm actually working, there's some really cool math in this, and I'm working with people at Microsoft and people outside of Microsoft, like John Hopcroft, who's a really good computer scientist, to try to figure out how to measure and guess how link farms distort the web, find things that look like that, and throw them out. Okay, don't take them in. Don't take those into account.
I've got a question on the in and out. By definition, doesn't every web page that has a link in, isn't that also a link out?
No, for example, on my web page, I could post a paper, okay? Or you could post an invitation to a party on your web page, okay? On your MySpace page, you could you could post an invitation to a party. Someone clicks on that, they go to this page, which is an invitation to a party. There's nothing out of that invitation, okay? But they could just push the back button. So the back button on your web browser walks backward over the link, okay? So, but any kinds of pages that you post, or when I post my academic papers on my web, there's just a link out to them, but unless I have links in my bibliography or something, they're not pointing out to anything else. Okay, so social power law networks. Well, a lot of sociologists have measured acquaintance networks, and they found that there are power laws, like Club Nexus Network at Stanford. Okay, well, this is drawn probably by this person because they see themselves as the center of the universe. There are different ways of plotting things, but it is true that this person in some way is, pretty highly connected in that universe. This is your social butterfly, okay? And then there are other people who are not so highly connected. Okay, so let's look at another example. Oh, no, this is, okay. So in 1929, the Hungarian author, and I wonder, I know there must be some Hungarians in this audience. I'm going to mispronounce this name. But anyway, Corinthi published a short story, and this was 1929, so it's really amazing, in which he proposed that every pair of people on the planet were separated by no more than 5 intermediaries. Now, this was just fiction, right? But then, in 1967, the psychologist Stanley Milgram empirically proved this. What he did was he went to, let's say, the Midwest, and he said, and he would find some person in the Midwest, and he'd say, here, I'm giving you a letter for an elementary school teacher in the Northeast, okay? And I want you to pass this letter to the person you think is most likely to get it to that person in the fewest steps. And then that person would have to do the same thing. And what he found is that there were 6 degrees of separation, that typically it took about, on average, 6 steps to get there, which is really amazing. I mean, that says we're much, we're much more connected than you might have guessed, okay? And that's especially true if I can figure out who I want to send it to. I mean, obviously, I'm not going to send it to my friend in Russia if I want to get it to an elementary school teacher in the Northeast, okay? But I might send it to a teacher I know in New York City or something. Okay, so here is the co-author network. There is a conference called InfoViz, and this is now a science, actually. When you have data sets, how do you visualize them, okay, so that humans can comprehend them? Okay, you have this whole set with all this data in it. How do you visualize it? And there's a workshop on that called the InfoViz workshop, and they had a contest in 2004 in which they said, what's the best representation, the most appealing visual representation of a co-author network, people who had written papers together. And this was the winning entry. And so these guys, what they did was the size was the number of papers that this person had written. So obviously, this person writes too many papers. Okay. And, or no, what is it? Is it... Okay, so I should read this more carefully. Yes, the node size is the number of papers. The node color is the number of citations, okay? And then these things cite each other. And you see, like, this community is totally separated from everyone else, okay? So this is a community which, if the grant applications went to each other in the community, they'd be in fine shape. If they went to anybody out here, these guys would be in a lot of trouble, okay? And so it turns out that this has a power law. Okay, romantic relationship network. So here's something from the American Journal of Sociology, and they just did heterosexual couples, and so they also left out the singletons, and so they have 63 monogamous pairs there, and then they have just interesting, so they have 12 of these, and they have, kind of interest. This is one where you worry about the spread of viruses, okay? Okay. And here is self-reported, okay, very important, self-reported sexual partners, okay, and it's on a log-log scale, and on a log-log scale, power laws come out as a straight line, and here it is, and of course the men report more than the women do, and who knows whether to believe them or them, but anyway, this is self-reported, okay? So these kinds of networks also have power law degrees. Okay, so models. For simplicity, I'm just going to look at models that explain the small diameter, the aging, the power law, but not the clustering. And these are called preferential attachment growth models, or rich get richer models. And there are undirected ones that describe the internet and co-authors and that kind of thing. And then there are ones for things like the World Wide Web, which have hyperlinks, okay, links that go from one site to another site. And so the non-rigorous work actually started back in 1925, but in 1999, people started to apply this to models of the internet. And so what this model is that at each time step, so it's a growing vertex, at each time step, a new node will come in, and it will send out, let's say, M connections to old vertices, and the probability that it will send out a connection to any given vertex will be proportional to the number of neighbors that already has. So this is why they call it the rich get richer. You walk into a room and you see that, oh, that person looks really popular, like all these people are talking to them. I think I'll go talk to them, okay, because they must be interesting. And so you go and you introduce yourself to that person because they must be interesting because everyone else wants to know them. And I know that some of you have kind of an anti, but you're not normal. Okay. So, which is good. Universities attract people who are not normal, which is why we love being in universities with each other. So we might actually not have that. We might have an anti. We might have a negative sign in front of that. But anyway, this is the rich get richer. People want to invest with people who've made a lot of money, and so those people then make more money. Okay, the rigorous work was done in 2001. Boabosh and Reardon showed that these things indeed do have small diameter. They showed that if you take this simple model and you have n sites, that the diameter grows like log n. So if you have, 1 million sites, which is really big, well, the log of 1 million is not very big. So the diameter is pretty small. It might even look like 16 if if n were not that big and you had a big constant in front of that. Okay, and then this thing that I told you before, when I told it to you, those other guys got it by something that a mathematician would call a back-of-the-envelope calculation. And the actual proof was longer, but they indeed did get this. So the probability that I have k neighbors goes like 1 over k cubed. The probability that I know 100 people goes like 1 over 1 million times some constant. Okay, the constant's probably pretty big. Okay, so then the directed preferential attachment model. Well, at each step, one of 3 things happen. So I was describing this to a patent lawyer, and I said, it's like flipping a 3-sided coin. And he wrote all this description of a 3-sided coin into the patent, which was kind of, I asked for another patent lawyer. He also asked me what an exponent was. So, okay. But the point is that one of 3 things happens, okay? And that's all that happens. And that's everything that happens. So it adds up to 1. And so with probability alpha, a new vertex is created and sends an edge into an old vertex, okay? So what is this? This is like I create a new web page and I send something to an old web page with probability proportional to how many things are already going into that old web page. The second thing is what we were talking about, 10 minutes ago, with probability beta, a new vertex is created. That's like you post your party thing on MySpace, you put a link to it, and it just goes out. And then with probability gamma, an old vertex sends an edge into another old vertex. So we're both, my website has been sitting around for a while, the IMA's website has been sitting around for a while. I send a link to the IMA's website. Well, if I send out a lot of links, then I'm going to have more of a tendency to send out links. So probability proportional to the number of links I have already sent out. And if the IMA has a lot of links into it, it's more likely I'm going to send a link into the IMA's website. So probability proportional to the number of links into that site. Okay, so that's all I want to tell you about models of these power law networks. Now we're going to talk about models for the spread of viruses and worms. And here it could be on any kind of network, not just a power law network. Okay, so we'll first talk about viruses and worms on computer networks. I'll tell you about some of the observed properties. And then we'll talk about two kinds of models for the spread of disease. One is called SIS, which is susceptible, infected, susceptible, and another is called SIR, which is susceptible, infected, or either recovered or removed. Okay, so viruses and worms on computer networks. Okay, a virus, so I'm sure all of you have heard of viruses and worms, and some people get them confused with one another. A virus is a program that has to be attached to a host program, so some kind of executable. This is why they say don't open up any attachments in your email, okay? Because then if you do that and there's a virus in that attachment, it will go into your system, okay? But if you don't run any executables, you can't get a virus. Okay, worms are worse than that. Worms are programs that break into your computer using some vulnerability. Now, what do I mean by that? I mean that whoever made your operating system might have made a little mistake, and they might have left some vulnerability in it, okay? They don't do that intentionally, okay? And given how complicated these systems are, there might be lots and lots of possible vulnerabilities. And so what happens is that it doesn't require any user action to spread. If your computer is on and a worm hits it, it's going to get it. You flip your computer on. That's why sometimes when I walk into my building and a worm has come out, people put signs on the elevators so that before you go up to your office and flip on your computer, you know that there might be a worm out there, okay? Okay. So here's what happened with the code red worm, which is one of the terrible early worms. So at 10 o'clock Greenwich time in 2001, July 19th, 2001, the code red worm started infecting unpatched versions of the Microsoft, of a certain Microsoft web server. So what does the worm do? The worm just generates random IP addresses. All of your computers have IP addresses. It just starts generating random ones. Some of them correspond to nothing, okay? But one of them might be your computer, okay? And so you flip your computer on and boom, if it's not patched, this is why they say when a vulnerability is found, you should patch it. Because if a worm takes advantage of that, it'll get in the minute you turn your computer on. Okay, so the worm spreads, as I said, by probing random IP addresses and infecting all the vulnerable hosts. Most of the IP addresses it comes up with are just nothing, okay? But some of them are real, and if they're unpatched, they're in trouble. Okay, so this worm infected about 360,000 hosts in 13 hours. Most of it happened over a period of 5.5 hours. So here it is, okay? And finally, it started to level off, and what was going on? What was going on was that they were starting to pull off the infected ones, and they were starting to patch the uninfected ones. Okay, so they pulled off the infected ones because those are now starting to infect everybody else, right? So the infection rate started to decrease, so here's the infection rate. Okay, so the rate goes down, so this levels off due to patching, rebooting, filtering, that kind of thing. Okay, now there's something much worse, and actually one of these has even come out, and these are mutating viruses and worms. So far, when I first wrote this, it was so far. Now there has been one mutating one. So the next big threat is a mutating virus or worm. So what would a mutating worm do? It would have a list of a lot of vulnerabilities. So let's say I found 100 vulnerabilities, and I didn't write separate worms for each vulnerability as I found it. I saved them all up, okay? And then what I would do is I would send this worm out, and it would start infecting machines, and then people would start, Microsoft would issue a patch, or they would have issued a patch already, but now you realize you better patch your computer. Okay, so you patch your computer before you put it online. And so people are patching to prevent getting infected by this worm. Then, at a random time, for example, or in response to some command, all of a sudden, there's now, they start out with one infected site. There are now 300,000 infected sites, and they go, okay, switch to the next one. Now, these 300,000 act as seeds, and they start sending things out for the second vulnerability. And now, you've got, I don't know how many, and after some time, so you never get that fall off, okay? Then it starts all over again. So that would be really, really bad. Okay, so it would not be possible to effectively patch against this. And there are similar problems with rapidly mutating viruses in the human population. For example, the HIV virus, okay? One of the big problems, one of the reasons there's no AIDS vaccine, no good AIDS vaccine, is because HIV is really, I'm wandering off your screen, aren't I? I'm making it really hard for you. It just occurred to me. Okay. The HIV virus is really rapidly mutating, okay? So by the time you might think of a way of controlling it, it's a different virus. In fact, there's a really, I don't know how I'm going to get through this, but anyway, there's a really cute story. We have a group at Microsoft that works on spam filters, okay? And they came up with a way of trying to adapt to mutating spam, because what would happen is you put up a spam filter, against like $3 signs in a row, or the word Viagra or something, and then people would do a variant of that, okay, a misspelling or something. And so this spam filter actually did reasonable changes, and so it mutated, and so it prevented things that weren't even being used yet. And these guys got in touch with some AIDS researchers and said, why don't we use this same thing to try to develop an AIDS vaccine? They've been working with some doctors in Australia, and they're actually on trials with monkeys now, and it seems to be doing pretty well. So anyway, but it's a big problem with HIV, okay? So models for the spread of viruses and worms. Well, for mutating worms, there's the SIS model. So each site is in one of two states. It is either a susceptible site, which means that it has a vulnerability that the worm exploits, so it can be infected, but it's not infected. It's healthy, but it is susceptible, okay? Or it's infected, and it's infecting others. Okay, so it's just two states. Non-mutating worms, you have the SIR model, which means that it's either susceptible, it has a vulnerability, it can be infected, or it's infected and it's infecting others, or it's removed, which means that it's immune, it's been patched, or it's recovered, or it's just pulled out of the network, so it can't infect anyone else. Okay, this one is easier to treat mathematically, and it also helps us to understand the worst viruses. Two states are easier to treat than three, and it helps us to understand these mutating viruses and worms. So we're going to look at that. There are two versions. There's a continuous ordinary differential equation model, which almost treats this like a fluid, this virus that's spreading. And there's really nice stuff on this on the web if you want to look it up. And a lot of people who actually work on viruses, when I've worked with some product groups at Microsoft, we actually have used models like this. The harder one to do is a discrete one. It's known also as the contact process. So what is it? Okay. An infected site gets cured, gets healthy, or recovers at rate rho. Okay, it's Greek letter rho here. Rho for recovery. Okay? Often that's just taken to be rate 1, but things can get cured, right? You get a virus, it doesn't mean that you're forever sick and infecting other people. Okay? And then a healthy site goes to an infected site at some rate beta times the number of infected neighbors. So, if I've been exposed to 3 people with the flu, I have a much bigger chance of getting the flu than if I've been exposed to only 1 person with the flu. Okay? And the relevant parameter is the infection rate over the cure rate. And the applications it's studied in probability theory and physics, and of course, in the study of the spread of diseases, epidemiology, and it was first applied to computer networks in 1993. Okay, and so this is the one that we're going to be using, not the ODE version. Okay, so most people, until relatively recently, had studied this on a bounded degree lattice. So what would that be? That would be something like a grid, like a checkerboard, okay? And so I'm connected to my 4 neighbors, okay? And I could have an infinite version of that. Or if I wanted it in 3 dimensions, I could be connected to 6 neighbors, north, south, east, west, up or down, okay? And what was found is that there was a critical value, lambda, such that if the infection rate over the cure rate was less than that, the infection was going to die out with probability 1. It might infect some people, but eventually it would go away, okay? But if lambda was bigger than this, then the infection would survive with positive probability. It would remain in the population forever, okay? And we see this in certain cases, right? Okay, now what if, so this is called the epidemic threshold. Okay, what if instead of an infinite checkerboard, I only had a finite piece of a checkerboard? Well, if I had only a finite piece of a checkerboard, it might happen that everybody gets cured at the same time, okay? Odds of that are not high, but it could happen, okay? So you know that the infection is going to die out eventually, but how long does it take to die out, okay? Does it die out in a relatively short time or in a really, really long time? And it turns out, and this kind of thing comes up in computer science all the time, the important difference is polynomial time versus exponential time, okay? And so if you're less than this critical value, then the infection will die out in a time which is polynomial in the number of squares on your checkerboard, whereas here it will last an exponential time in the number of squares on your checkerboard, which is really bad because, you might just be dead of old age by the time the exponential time has happened. Okay, so what about preferential attachment graphs, which don't look anything like these checkerboards? Okay, so we're finally on the last part of the talk. This one's going to become a little more mathematical. What I'm going to do is I'm going to take this model, this SIS model, and I'm going to put it on those preferential attachment graphs. I'm actually going to state some theorems for you in math, but translate them into English. Okay, so we'll first talk about the spread of epidemics in the SIS model. This is the susceptible, infected, susceptible, what we do for mutating viruses on these kinds of graphs. And then we'll talk about the containment. So what do I mean? First thing I'm going to do is ask, what is the epidemic threshold of these power law graphs, like these social networks or these networks of kids in high school? Okay? And is there a way of distributing antidote to these kids in high school, other than celibacy, which would be like quarantine, To increase the threshold, that is to contain the epidemic on a general graph. Okay, so it turns out that in preferential attachment graphs, remember, this is like your internet, your World Wide Web, your network of relationships in high school, for any positive rate of transmission to the neighbors, no matter how small, there's a positive probability of an epidemic. That threshold is 0. No matter how small the rate of transmission, if you have a graph like this, what's going to happen is that the infection is going to have a positive chance of taking off and just not dying out, okay, or not dying out for a super polynomial amount of time. And the rigorous proof was done by us in 2004, and we even could tell you about the survival probability, which I will, but if you don't like that, you don't have to listen, okay? So we considered this model on a preferential attachment graph of size n. Now what I'm going to do is I'm going to tell you also about the difference between typical and average, okay? And you might hear people, those of you who are not mathematicians, may hear in the news people say typical and average, and often they use them interchangeably, and sometimes you can use them interchangeably, and sometimes you really can't. And if you have a very tight distribution, typical means, you know, I just pick anybody, and that's, it's like for that typical person, this is what happens. And if you have a really tight distribution, then typical and average are pretty close. But if you have some possibility of somebody really like out there, okay, then that really out there person can, or that really out there website can have such a huge effect that it throws off the average. Then typical and average won't be the same. So what I'm going to do here is I'm going to throw away some really small fraction of my websites, and I'm going to start it off at one of the other ones. And it turns out that it will survive a long time with a probability. Now this looks terrible, doesn't it? Lambda is small, okay? So 1 over lambda is big. So log of 1 over lambda is still pretty big. Lambda is a small number, I raise it to a big power. Small number raised to a big power is small. But the important point is that it's positive. That tells us lambda c is equal to 0. Why? Because no matter how small the rate of transmission, there is positive probability that it is going to take off and last longer than you live, okay, or longer than your computer lives. So the translation is, even if we leave out a few highly connected vertices for any positive rate of transmission, no matter how small, there's a positive probability of an epidemic, so mutating infections are going to spread. Okay, and you see that with mutating viruses and worms on a computer. You see that with the AIDS virus. Let's hope that the bird flu virus isn't mutating that quickly, because then you would see that. I mean, you might not have something that mutates that quickly, but the more it mutates, the faster it mutates, the more it's going to act like this. Okay. Okay, so typical versus average. I left out this many vertices. So if there was 1/10 of a chance of transmission, I left out 1/100th of the vertices. Okay, 1/10 squared of the vertices. So what's the effect of these vertices on the average survival probability? And it's really dramatic. So here's the second theorem. It looks almost the same, except here I don't leave out anything. And what I get is this is the probability that it survives, and this number is much, much bigger than this number. Why? Because this is a small number raised to a constant. This is a small number raised to a really big power. Small numbers raised to big powers get really small, okay? So what happens is that if I start something from the MySpace website, okay, or the AOL website, as opposed to, you know, Joe Schmo's website, there's going to be a much bigger chance that it's going to survive for a really long time. So these terrible people who want to get something to spread, if they started spreading from something very highly connected, then it's going to last a really long time. Okay, the final topic that I want to cover is how do we contain this? It's a little technically complicated, but I want you to think about having a certain amount of antidote, like, you know, you've got a virus and you've got a certain amount of Tamiflu, okay? So that's what I want you to keep in mind. So the question is, what is the best way to take a fixed amount of antidote and put it among all my sites to raise the epidemic threshold, okay? What I want to do is I want to make it so, let's say, well, okay, we know the epidemic threshold is 0. What if I could raise it so that it was, you know, 0.5? Well, that would mean that if the rate of, if the constant in the rate of spread was 0.2, you wouldn't get an epidemic, right? Okay, so this is something that we also did. So the program, I'm going to review the definition of the model. I'm going to give you, this is going to be the most technically complicated part, I'm going to give you some more details about the behavior of that, but I'll try to explain it to you in an example. And then I'm going to let rho vary from one vertex to the next. So rho was the recovery rate, which you could think of as almost giving one or rho doses of antidote to each person. Okay? Yeah?
Could you show us theorem 1, please?
Well, I go back and show you theorem 1, yes. Back. Okay. So what I told you in theorem 1 was that lambda c was equal to 0. I didn't tell you how fast it went to 0. Now I'm going to tell you something about how fast it goes to 0, and then I'm going to try to distribute my antidote to make it go to 0 more slowly, or maybe not go to 0 at all. Okay? So, where are we now? Okay, so how do we distribute this antidote? Okay, so we're going over, so this is the review of the model, same as before. We go from infected to healthy, we get cured at rate rho, and we get infected at a rate beta times the number of neighbors. So, you know, if you sleep around, you have a bigger chance of getting infected. Okay, so details of theorem 1. Okay, so first, I'm going to do theorem 1 on a graph which is called a star, okay? So what is a star? A star is one central site and lots of sites which are all connected to it but not connected to each other, okay? And this tells you in theorem 1, but I hadn't told you before, how this goes to 0. This looks terrible, but what does this mean? Let's say n were 1 million. I had 1 million people, okay? Then, if I didn't want the epidemic threshold to be 0, how big would rho have to be? Well, I'd have to make this like, so this is n to the minus 1/2. So this is like 1 over 1,000, which is the square root of 1 million. So this would have to be 1,000. This would have to be n to the 1/2. And what this is telling me is that the amount of antidote that would be required would be 1,000 units per person in order to make this epidemic threshold not go to 0. So I have 1 million people, okay? Yes, so I have 1 million people. But if the people were connected like a star, okay, then what would happen is that I would, you know, cure them. Somebody would infect the middle again. The middle would stay infected for such a long time that it would infect some others. It would get cured, but by the time it got cured, tons of other people would be infected, okay? So what would you do in that case? Well, you can already tell me what to do. Give more of my antidote to the one in the middle, right? Right? I know, people are telling me what the person in the middle is, right? I see people whispering who the person in the middle is. Okay, I don't have to know who the person in the middle is. Okay, for preferential attachment graphs, I can't tell you how, but it still goes to 0. So what is this telling me? If I have 1 million people, I need 1 billion doses of antidote if these people are like a star. And if they're like a preferential attachment network, it's not quite 1 billion, but it's still superlinear. So now I'm going to vary my recovery rate. So I'm going to have the same total amount of antidote, okay? The same as the number of people. So I have 1 million units of antidote, not 1 billion. I've got 1 million. I want to see if I can possibly push this epidemic threshold up. Okay, so I've got some Tamiflu. So what's the best policy to control the infection? And I've just got 1 dose per person. Okay, so what an epidemiologist would do is contact tracing. Okay, if your kid is in a class and some other kid in the class gets the measles, they say, oh, your kid has been in contact with a kid who hasn't, your kid should get a shot so that they won't get the measles, okay? Or, you know, if they find that someone has a venereal disease, then the standard procedure is they ask who are the partners, and they go and they give antibiotics to those partners. Okay, that's called contact tracing. You trace the contacts of the infected individuals. Okay, and if things were mutating all the time, you would have to give a number of doses of antidote, which is proportional to how many of your infected neighbors, how many of your neighbors are infected, because they all might be infected with a different version. Okay, so you might need a dose of Tamiflu for every version. Okay, so if I did this, if I gave it out proportional to the number of infected neighbors, unfortunately, this thing would still go to 0. Go to 0 a little more slowly. Now, it's going to 0 like n to the minus 1/3. I got 1 million people, okay? Now I need n to the plus 1/3 units per person. I need 100 units per person instead of 1,000 units. So contact tracing is a lot better than just giving 1 dose of Tamiflu to each person, okay? But still, it's not going to help me, okay? It's an improvement, but beta C still goes to 0. So it takes a superlinear amount of antidote, okay, more than 1 unit per person, a lot more, to control a virus via contact tracing, which I find pretty disturbing because that is how we normally deal with epidemics, okay? And we're acting as if they're epidemics on very different kinds of networks. Okay, so now let's, and it'll just be a few more minutes. I'm going to take something in which the cure is proportional to the degree, not the infected degree. This is a lot easier, okay? The infected degree changes all the time, and I've got to know who's infected and who's not. Let's say I just said, okay, I am going to inoculate the people who come into contact with tons and tons of other people. You know, so I'm going to give people who come into contact with tons and tons of, like when I was a professor at UCLA, they said to me, you're in contact with hundreds of students, you should get a flu vaccine, okay? Or in some countries where prostitution is legal, they are always giving antibiotics to prostitutes because they say it doesn't matter whether this person is infected or not, they have a very high degree. Okay, so does this work better? And don't look at the details of the theorem, but what it says is that it does work. It pushes the threshold up so that we have a positive threshold, okay? So if you cure proportional to the degree, so if you just say, the problem with contact tracing is by the time you're trying to stop the epidemic, it's out of control. You think you're doing an intelligent thing by looking at who has the disease, okay? But it's already out of control by the time you're doing that. Better to anticipate it and inoculate against it. So this works, and then the final question that I have is, can we do something better? I push the threshold up to a positive value. Can I push it all the way up to infinity? So no matter what, I won't have the spread of this virus, okay? And the answer is no for special grafts, which are called expanders, okay? What are expanders? I'm about to put a definition up there. What you should think of is this. An expander is something which has about as much boundary as it has a volume. Okay, most things that we know, you know, like a grid or a cube have a lot more volume than boundaries. A cube grows, okay, in 3 dimensions, the volume grows like n cubed, the boundary grows like n squared, okay? An expander is not like that. An expander, the volume is, the boundary is really growing. And so, roughly speaking, I think of an expander as something that I can't quarantine. Because how do you quarantine? You cut off interaction with the outside. Well, how are you going to do that with an expander where the number of interactions that you have to cut off is so huge? In certain countries, you can do this. Like in China, actually, they quarantine whole universities when the flu broke out. Nobody was allowed to leave the university campus. But if you're not basically a totalitarian state, then you can't quarantine and expand it. Okay, so that's a condition. What this final theorem says is that for expanders, okay, these kind of preferential attachment graphs, these social networks, you know, the internet, the World Wide Web, those are expanders. No other inoculation scheme can do more than a constant factor better than inoculating according to the degree. Okay, so you can push it up somewhat. You can say, I'm not only going to consider, you know, how many neighbors I have, but also how many next nearest neighbors I have, but you can't get rid of it. So the summary is that on preferential attachment graphs, which are like the internet, the World Wide Web, the high school dating network, mutating viruses and worms with any positive rate of transmission will become epidemic. Okay? Contact tracing does not control the epidemic in the sense that the threshold for the epidemic is zero, is zero on a star and also on preferential attachment graphs. But on a general graph, curing proportional to the degree does control the epidemic in the sense that it at least gives us a region. If the probability of spread isn't too large, we're not going to get an epidemic. And nothing is going to do more than a constant factor better than that with an expander, which are the kinds of social networks and technological networks that we have. And that's it.
Okay, thank you very much. I wanted to mention that on your way out, if you're interested, we have some of these postcards that you can have as a souvenir. And also, if there's any students who need a certificate of attendance, they're over here. And I think Jennifer would be willing to take a question or two. Are there any?
Yeah?
I have a question about the inoculation schemes that propose the contact tracing scheme versus the inoculation by degree.
Mm-hmm.
Both of those, for the degree inoculation, that assumes a fairly limited spread. Is that right? You can sort of catch it before it blows up.
I can prove that you will catch it before
Can you
it blows
repeat the
up.
question?
Oh, yeah. So he said that what I was assuming with the inoculation just by degree was that I could catch it but before it blows up. And what I'm saying is, I mean, what's kind of nice about mathematics, I actually have a mathematical proof that I can catch it before it blows up.
The question I have is, if you need to sort of catch it, how is that significantly different from the contact tracing, which will also only work if you catch it at an early phase?
The contact tracing, it depends how many doses of antidote you have. If you have enough doses of antidote, then you can catch either one of them, okay? But you're going to have to catch it at a much, much earlier stage with contact tracing. And it's going to be almost impossible to do it if N is large. Okay, I'd love a question from a high school student. Is there a high school student here? Are you a high school student? Well, anyway, you got your hand up. Okay.
So lately on MySpace, there's all these viruses, and I don't know how you get them, so how can you prevent them?
How can you prevent them? Celibacy? Seriously, though, I mean, this is kind of what I'm saying here. What I'm saying is that these social networks or these technological networks, which are based on social networks, it's very, very hard to prevent them. You can be a person that nobody likes and nobody connects to you, and you don't connect to anybody else. So, I mean, I was kind of kidding with celibacy, but I wasn't. You know, it doesn't work too well. I mean, I can quarantine you if you're very unpopular without cutting too many links. But my guess is probably I'd have to cut a lot of links. And so what I'm saying is that you're actually not in good shape. You're going to need to be getting rid of the virus, giving yourself a dose of the antidote, cleaning the mess up, very, very often, like, you know, n to the 1/3 time, and my space n is really big. Okay, so let's hope there's a small constant in front of that. Okay. Okay, any other questions? Yeah?
How do they address the question of these infections in very dangerous cases like national security?
Well, in national security, I think, I mean, we're actually really concerned about that, right? We're really concerned about where we should, how we should distribute Tamiflu. I mean, there are all kinds of questions about, you know, if we have a certain amount of antidote and somebody, you know, antagonistically comes in there and tries to start an infection, where should we have it to catch the infection soon enough? And that's one of the reasons to do things like this. And, you know, I'm doing this like a theorist in the sense that I say, well, you know, you can't do more than a constant factor better. People in real life care about a constant factor, so they would be trying to do that. And as I said also, there are some places where they actually do quarantine, and quarantine works, but you really have to cut a lot of interactions. You know, cut so much that it no longer looks like these power law networks anymore. Yeah?
So are you suggesting that on, say, a national ID card, we should list the number of people we know?
And then it would be self-reported too, so there'd be another question there. Well, I'm saying that we might be able to study networks and see how many people you know, right? We might be, and this is terrible, but it's true. I mean, there are, if you have Gmail and Google Toolbar, or if you have Hotmail and an MSN toolbar, you know, there is information somewhere that exists that tells me a lot about your networks, okay? What you do on your website and with whom you interact. And once the world is filled with sensors, I'll know about where you're going. And let's hope that we don't, well, I mean, I think the cure, quite literally, is worse than the disease there. But anyway, I mean, we might be able to monitor these networks.
So do you assume one operating system, or should we diversify?
What makes you say that? So all that does is, I mean, that obviously makes it smaller, okay? That cuts down on N. I'm sorry, she wanted to know if it would be a good idea to have many operating systems instead of just one. However, as the many each get to be pretty large, and we've seen this, right? We've finally seen some viruses and worms on the Apple operating system. When it gets to be big enough, then these things do start spreading. So, you know, yes, for the control of viruses and worms, it's good to get N down, okay, obviously. I'm looking for other solutions for some reason. Okay.
Okay. Thank you very much. Keep your eye on the virus-free www.